Hello everyone, my name is Marissa Loving and I'm an NSF postdoc at Georgia Tech. And today I'm going to be telling you a bit about n-periodic homeomorphisms and volumes of mapping tori. This is part 2 of a 2-part talk on these topics. And this talk is going to sort of focus more on the second half of my title, in particular volumes of mapping tori. If you're interested in hearing a bit more about n-periodic homeomorphisms and some background material, feel free to check out part 1. Much of the content of this talk, I should add, is joint work with Chris Leininger, Elizabeth Field, and Hee-Jung Kim. So the outline of this talk is as follows. I'll start by just reviewing very briefly the definition of n-periodic homeomorphisms. I'm going to introduce a notion of irreducibility. I'll give some examples, and I'll sketch the proof that the examples are irreducible. And then in the final part of the talk, we'll focus our attention on volumes of 3 manifolds and make some connections between the dynamics of surface homeomorphisms and the geometry of 3 manifolds. So just as a reminder, in case you didn't see the first talk, when I'm talking about n-periodic homeomorphisms, I'm talking about homeomorphisms F of an infinite type surface S, which satisfy the following. And I'm just going to give the hand-wavy definition here, which is more than enough to sort of take us through the talk, which is that we want that each end of our surface S is either attracting or repelling under the action of F. So either under forward or backward iteration. Okay. And the notion that I want to introduce in order to sort of further study these n-periodic homeomorphisms is this notion of irreducibility. So I'll say that an n-periodic homeomorphism F is irreducible if it has 1, no reducing closed curves. Okay, so by reducing closed curve, maybe it'd be helpful here to draw a picture. Let's just draw sort of a simple picture, the ladder surface. Okay, and I'm going to consider a curve, say that we have a reducing curve would be a curve that sort of comes in from the end and then just sort of moves through my surface. So for example, a curve like this that just sort of moves in one side and out the other. So it moves from a repelling end to attracting end. That would be a reducing closed curve. I also don't want there to be any reducing lines. So a reducing line is going to be a line that passes between 2 distinct ends. So for example here, something like this, where of course this is sort of keeping on going in each direction. I could also sort of consider a reducing line on, say, a slightly more complicated surface. For example, if I look at a tripod surface. Okay, and if I consider sort of having 2 shifts that are sort of coming in from this end, so this is here is the attracting end, and then we have 2 repelling ends here. Okay, so I could have also a reducing line that goes, for example, from a repelling end to a repelling end. Okay, and then I also don't want there to be any periodic curves. So a periodic closed curve is sort of like a reducing curve, except instead of sort of just flowing from one end out the other, I also would want to sort of not have any curves that, say, bounce around in some compact region. So for example, I wouldn't want to have a curve like this that maybe gets sent to here, and then gets sent to here, and then to here, and then back. Okay, so like this little sort of cycle. I'd think of that as being like a periodic curve. So I don't want anything like that happening. And my goal for this talk is to really show that these irreducible n-periodic homeomorphisms are in many ways analogous to pseudo-Anosovs. Okay, so that's one of the things I hope to demonstrate, at least to some extent. But first, I want to give some examples of irreducible n-periodic homeomorphisms. So these are examples that come as joint work with Hee-Jung Kim, Elizabeth Field, and Chris Leininger. And so this example is sort of going to combine 2 different homeomorphisms. So I'm going to consider a homeomorphism called a handle shift. Okay, so this is sort of just moving each handle over by 1. And then I have sort of my compact subsurface C. Here I have just this sort of genus 2 subsurface. And I'm going to consider some partial pseudo-Nasav on this subsurface. So let A be a partial pseudo-Nasav. On C. Okay, and what we show is that the composition F equal to rho H is an irreducible so that's key and periodic homeomorphism. And so this is sort of a single example that I've shown here, but we actually can show this sort of for any infinite type surface with infinite genus and finitely many n's accumulated by genus. We can provide examples of these irreducible and periodic homeomorphisms with sort of any given n behavior. Okay, so I won't get it too far into the proof, but I do just want to highlight a couple of the tools that we used. Okay, so the main tools that we use are sort of familiar tools for studying homeomorphisms of finite type surfaces. So we use subsurface projection, as well as using the fact that this pseudo-Nasav acts on the curve complex of C with large translation distance. So this is something that we asked. So here, this is the curve complex. Really, we just need the curve graph of C. Okay. And I won't get into too much detail here, but I'll just sort of add a third point, which we use, which we get to sort of show that this boundary of C, so let me highlight them. So here's one boundary, here's my other boundary, highlighted in pink. So boundary C, okay, that this boundary sort of acts as a buffer which prevents sort of curves from escaping from one end out the other. So I'll just sort of write it. This is very informal, of course, but sort of gives a little bit of the sort of idea of what we're doing. We really just show that these boundary components are sort of filling up that subsurface. Okay, so this is sort of the sketch of proof, as sort of hand wavy as possible, sketch of proof, which we use to show that there are no reducing curves. And again, this is sort of using these ideas of subsurface projection and sort of this extra requirement on what the translation distance of H is on this curve graph. Okay. So now I want to sort of connect these irreducible and periodic homeomorphisms back into this sort of larger picture of this connection that we can make between dynamics of homeomorphisms and the geometry of three manifolds. So I'll start by just sort of the biggest, sort of broadest possible connection, which is probably familiar to many, which is just this very famous theorem of Thurston. Okay, so this was sort of a first step in the hyperbolization, geometrization conjecture, which is that the mapping torus F, is hyperbolic. So we talked about mapping tori a little bit in part 1. In case this is not familiar, feel free to check that out. That the mapping torus is hyperbolic if and only if the monogamy, so sort of our gluing map F, is pseudo-Nasav. Okay, so this is sort of tying this sort of very large-scale dynamics, the fact that F is pseudo-Nasav, to sort of the large-scale geometry right, of this 3 manifold. But of course we could ask, well, can we capture sort of finer data? Okay, so what about finer geometric data? Okay, so let's talk a little bit about what I mean by that. Okay, so pseudonosovs, right, come with these are equipped with these underlying foliations, right, these transverse singular measured foliations on the surface. And our pseudonosov sort of acts with prescribed dynamics, right? It stretches along one pair of foliation and squeezes along the other. And that sort of term that it's stretching or squeezing by is something called the stretch factor. So if we have, I'll just say F from S to S is pseudonosov. Let me actually just denote this PA, so I don't want a space there. Okay, then this stretch factor, right, we often denote it by this lambda of F. This is some real number greater than 1. Okay, so this is, I would call this sort of some fine geometric data that we can get about our homeomorphism. What else could we do? Well, we could also consider sort of the way that this homeomorphism acts on sort of other spaces. So for example, we could consider the translation length on Teichmuller space. Okay, and this really actually sort of leads me to two things, to two quantities, right? We could consider the translation length on Teichmuller space with the Teichmuller metric. Okay, which in fact turns out to just be described by the logarithm of the stretch factor. Okay, so we sort of is related very closely to that stretch factor. But we could also consider Teichmuller space with a Weil-Petersson metric. Let's see if I can spell this right. I always want to leave off one of the S's. Okay. Okay. So these are just a handful. Of course, there's sort of many other pieces of dynamical information that we could sort of choose to keep track of. But these are a few sort of examples of the types of things I have in mind. Okay. So here we have some sort of finer dynamical data. So what sort of finer geometric data could we keep track of? Well, I've sort of given it away here, right? We could keep track of the volume. Okay, we could sort of hope to relate the volume. And there's sort of lots and lots of work in this direction, so I'll just sort of write down a very few handfuls. And my apologies if your result is left off of this list. This is just the smallest sampling, which is just to illustrate that there's sort of been lots of work done to sort of build these connections. Okay, so there's work of Brock and Bromberg, work of Agel, Leininger, and Margolite, work of Kojima, Kin, and Takasawa, and the list goes on. Okay, but I'd like to highlight sort of one specific theorem. So this is a theorem of Kojima and McShane, which sort of makes clear the type of connection that I'd like to have between these sort of two types of information. Okay, so I really like their statement. It's quite clean, which just says that if we have some pseudonosov F, so if F is pseudonosov, then the logarithm of the stretch factor of F, which as we know, this is, right, our translation distance on Teichmuller space, this is bounded below in terms of, well, some sort of multiplicative factor given in terms of the Euler characteristic of my surface, but then just the volume of my mapping tori. And so here I'm able to give a sort of an upper bound on this sort of scaled volume in terms of this sort of dynamical property of my homeomorphism. Okay, so that's sort of the direction I want to go for the sort of next chunk of my talk, is to try to sort of dig more into this sort of type of relationship. Okay, so in particular, I also want to highlight this result of Jeff-Brock, which gives us a way of relating for some pseudonauts of phi, the volume of my mapping torus with the translation distance on the Pants graph. Okay, so here, this sort of tilde just means that, in fact, Jeff showed that these two quantities are comparable. Okay, so we have some upper and lower bound in terms of the translation distance on the volume. Okay, and so here, this Pants graph is the graph whose vertices are given by Pants decompositions. So I'm just sort of taking some disjoint collection of simple closed curves on my surface, which chop up my surface into pairs of Pants. And my edges are given in terms of these sort of two different elementary moves. One of them happening on one-hole torus. So I'm going to take this curve and flip it to this. Okay, so for example, I could take this curve and flip it to this one. That would be sort of that type of move. Or happening on a four-hole sphere. So taking this curve and flipping it to this one. Okay. And the reason, the sort of way that this result relates to my last slide, is that this translation distance of phi on the Pants graph actually is related to the Weil-Petersson metric. Right? It's related to the translation length of my pseudo-Nassau on Teichmüller space equipped with the Weil-Petersson metric. Because another result of Jeff tells us that this Pants graph is in fact quasi-isometric to Teichmüller space with the Weil-Petersson metric. So this is sort of giving us, this gives us a coarse model for Teichmüller space equipped with the Weil-Petersson metric. So this sort of is in the same flavor of results that we were just talking about. So in case you haven't seen or thought about the Pants graph before, here's just a very tori little path in it, where I sort of start off with one of my Pants decompositions of my genus 2 surface. I do a Pants move that happens on a full-hole sphere. So I take this curve and I flip it to this one. And then I do one of my Pants moves that happens on a one-hole torus, and I take my curve over here and flip it around to here. Okay, so here's just sort of a little toy piece in my Pants graph. And so I'm not going to get into actually the proof of this of Jeff's result, but I do want to illustrate just very briefly an idea of the proof of the upper bound that was actually given by Agel. Okay, and so the idea for this was to sort of build a model manifold for my mapping torus out of these sort of pieces called Pants blocks, each of which corresponds to a Pants move. That's an edge in the Pants graph, one of these elementary moves, and has bounded volume. Okay, so I've drawn my Pants blocks here. And this argument is actually really similar to Minsky's model manifold construction, which was used by Minsky and Brock-Canary-Minsky in the proof of the ending lamination conjecture, if that's something that you're familiar with. Okay, so there are my Pants blocks. And it'll become clear in a little bit why I sort of wanted to highlight this specific proof, because this sort of plays in to my result. So this next statement, this is sort of our main result, together again with Elizabeth, Heejung, and Chris, where we showed that now, if we start with an irreducible and periodic homeomorphism, we can also sort of give a bound in the volume in terms of this translation distance on the Pants graph. Okay. And here, you may notice something a little different happening. Right here, when we talk about the mapping torus, so I'm not actually just talking about the mapping torus, because if I look at the mapping torus of one of my sort of m-periodic things, sort of here I've given an example, I'm going to get this sort of cusp manifold. And so instead I'm going to look at this sort of compactified piece, M phi bar. Okay, so I'm going to look at this convex core instead. And we're able to give this upper bound, right? So this is not as quite as good as Jess, right, where we had this sort of comparable, but we're able to give this upper bound in terms of the translation distance. And in fact, we're able to show that this upper bound is asymptotically sharp. So we're able to sort of construct a sequence of examples where this volume sort of is going to infinity, and the ratio of the volume of our manifold in this sort of sequence to the translation distance on the Pans graph is going to some fixed constant. Okay, and so I'll just sort of end with an idea of the proof. Okay, and really the proof is sort of following the footsteps of Agel. We build a model manifold for now M phi bar, and again we're sort of using our Pans blocks to build this. And then we construct a homeomorphism between our model manifold and M phi bar, which is sort of arising as a quotient. And then sort of course, to show the sort of asymptotic sharpness, we build this sequence of examples, which is sort of asymptotically realizing the bound. Okay, and so I'll go ahead and end there, again with my picture of my n-periodic Ka, and thank you all so much for your attention.